Now recognize Dr. Lewis for 5 minutes to present his testimony. Dr. Lewis.
Chairman Smith, Chairman Weber, Ranking Member Grayson, members of the subcommittee, thank you very much for the opportunity to discuss this very exciting and timely research area of artificial photosynthesis, which is the direct production of fuels from sunlight. Artificial photosynthesis has the potential, indeed, to be a game-changing energy technology, cost-effectively producing fuels that are compatible with our existing infrastructure and providing us with both energy and environmental security. Artificial photosynthesis is inspired by plants, except that it can be over 10 times more efficient than natural photosynthesis, avoiding the need to trade food for fuel and producing a fuel, unlike lignocellulose, that we can directly use to power our vehicles, to potentially make ammonia for fertilizer to feed people around the world, and for other uses that they may develop. Solar fuels production would also solve massive grid-scale energy storage, so when the sun doesn't shine at night, we can still provide power to whenever people need it, and carbon-neutral transportation fuels, which are both critical gaps at present that research is needed to obtain a full carbon-neutral energy system. Artificial photosynthesis does not look like a leaf, nor does it look like a solar panel. Instead, imagine a high-performance fabric that could be rolled out like artificial turf. Supply that with sunlight, water, and perhaps other feedstocks from the air like nitrogen or carbon dioxide, and produce a fuel that gets wicked out into drainage pipes and collected for use. It's that simple in principle. Many approaches to solar fuels are being pursued. Some are taking biological molecules like the green pigment chlorophylls and using them coupled to man-made catalysts. Others use all inorganic materials like semiconductors at the nanoscale and couple them to catalysts like ones used in fuel cells. Still others use metal complexes as dyes and couple them to molecular catalysts. Laboratories like mine at Caltech have already demonstrated functional solar fuel systems through advances in nanoscience that have enabled us to fabricate nanofibers of semiconductors that can absorb light and couple them to catalysts all in a piece of plastic. So we know this is possible, but we need to continue to innovate and perform fundamental research to make it practical. A full system of solar fuels needs 5 components: 2 materials to absorb sunlight, one to capture the blue part of the rainbow, the other to capture the red part of the rainbow, to make it very efficient. We need 2 catalysts, one to oxidize water from the air, to provide electrons to make the reduced catalyst make the fuel that we want to harvest. We also need a membrane to separate those products to ensure that the system is safe and doesn't explode. We actually have all of those pieces. What we don't have is all of those pieces all working together seamlessly in one system where they all are stable and mutually compatible. Research opportunities include the use of high-performance computation to design new catalysts, to design new semiconductors, and to do modeling and simulation to help us understand how to make the system work as a whole, not just the pieces. Many approaches are useful, and many fuels could be produced. We might produce a liquid fuel directly. We might produce a gaseous fuel and then convert it to a liquid fuel. We might think about a solar refinery the way we have an oil refinery, where in comes our solar crude, and then we convert it to various fuels as the output using the same chemical processes that we use today. In closing, I also would like to make 2 points. One is that many other countries now have burgeoning efforts in solar fuels. There are large efforts starting in Korea, Japan, China, Sweden, Germany, and the EU. We should beneficially leverage those efforts We're well positioned to do that given our historical leadership in solar fuels in the United States. The second point is that solar fuels is an intellectual challenge that stimulates our young scientists, our graduate students, our postdocs, involving nanoscience, material science, and fundamental research in energy broadly to give us better options for energy technologies than the ones that we have now. Thank you.